We've reached that happy point in these series of lectures where we start talking about dark energy as well as dark matter. Dark energy is something different from dark matter. It is discovered in different ways, it plays a different role in the cosmic story, it comes from something different. So the fact that we need both dark energy and dark matter to explain the observations that we see in cosmology is evidence that the dark sector of the universe, 95% of what the universe is made of, is interesting somehow. It's not just all the same stuff. It might be that someday we can subdivide the dark sector into more than 2 bits. But right now, we think that dark matter plus dark energy is enough to explain everything we have been able to see in the universe so far. However, the way that we get to the discovery of dark energy goes through thinking about dark matter. The thinking about dark matter goes all the way back to the 1930s, when Fritz Zwicky was looking at the dynamics of clusters of galaxies. Zwicky noticed that in the Coma cluster of galaxies, the motions of the galaxies were too fast to be explained just on the basis of the ordinary matter that you saw there. In the 1970s, Vera Rubin looked at individual galaxies and realized that they also were spinning too fast to be associated with nothing but the visible matter. So through the 70s and through the 1980s, people became absolutely convinced that there was something called dark matter, that the dark matter couldn't just be the ordinary matter that was hidden from us somehow. But the question remained, exactly how much dark matter is there? Every time you look at a bigger and bigger system, you found more and more dark matter. In the 1980s, therefore, a lot of people were convinced that we would continue to find more and more dark matter. For example, you can look at individual galaxies and clusters, but how can you be sure that there isn't more stuff that is in between the galaxies and clusters? How can you be absolutely sure of that? Furthermore, there was another reason to be skeptical, and that comes from the Friedmann equation and the notion of the critical density of the universe. So look again at the Friedmann equation, which relates stuff in the universe to the curvature of space-time in the case of an expanding, smooth, homogeneous universe. On the left-hand side, you see rho. The Greek letter rho stands for the energy density of the universe. And now we're working again in the approximation where everything is perfectly smooth. On the right-hand side, you see the Hubble constant h, which is telling us about the expansion rate of the universe, and the spatial curvature k. So if k is 0, if space is flat, if geometry is like Euclid said it was, that's a special value for the spatial curvature. It could be positive or negative. The other terms in the Friedmann equation should not be positive or negative. They want to be positive. The energy density is something that should be positive. We like positive amounts of energy, not negative amounts of energy. That's dangerous. The Hubble constant squared, doesn't matter what the value of h is, it's never going to be a negative number. You square something, you get a positive number. So there's no special, particularly interesting values of the energy density rho or the expansion rate h, but there is a special, interesting middle value for the spatial curvature. It's 0. However, when you plug in the numbers, the energy density that we observe in the universe, in matter, in clusters and in galaxies, doesn't seem to be equal to the special amount of density you would need to make the universe spatially flat. We can define the critical density as the density rho that you would need to satisfy the Friedmann equation when k equals 0, when there's no spatial curvature. We can define that density whether or not that's the density we actually have. And in fact, cosmologists often define a number called omega, which is taking the actual density of the universe and dividing by the critical density. So if the density is equal to the critical density, we say omega equals 1. In fact, with the stuff that we found in the universe, the ordinary matter and the dark matter, only about 30% of the critical density is there in matter in the form of clusters and in galaxies. So omega seems to be 0.3. That's a very strange number to have, 0.3. 1 would be a very nice number to have. That would mean the universe is spatially flat. 10 to the 10, 10 billion, or for that matter, 1 over 10 billion, would be also numbers that wouldn't make you be surprised because they would just be some numbers. We can't really explain them. But 0.3 makes you think you're missing something. What 0.3 is telling you is that you're 30% of the way to being the critical density, and you remember that every time you look, you find more stuff. So throughout the 1980s, many cosmologists were convinced we would continue to find more stuff. We would eventually find enough matter in the universe to show that the density was equal to the critical density. 0.3 is close to 1, but it's not equal to 1, a lot of people just said, well, we haven't found everything yet. However, in the 1990s, that point of view became harder and harder to stick with. Technology became better. Our ability to measure the energy in the universe in terms of matter became more and more convincing, especially with things like gravitational lensing, with X-ray maps of clusters of galaxies. We became convinced that we had found the matter in the universe. It wasn't adding up to 1. The idea that a cluster of galaxies is a fair sample is exactly the idea that the amount of dark matter in that cluster compared to the amount of ordinary matter is the same in that cluster as it is for the universe as a whole. And if that's true, the amount of stuff that we were finding in clusters of galaxies implies that omega is only 0.3. It is only 30% of the critical density, does not quite equal 1. So if you were a respectable theoretical cosmologist in the 1990s, you would have begun to admit that this was true. But I can tell you that there were very few respectable theoretical cosmologists. The observers who actually took the data were becoming convinced that something was going on, but the theorists were clinging to the hope that somehow omega was equal to 1. I can remember personally giving a talk at the end of 1997, in December 1997. I was asked to give a review talk on what are the cosmological parameters, what is the Hubble constant, what is omega, the density, and so forth. And I was one of these disreputable theoretical cosmologists. I was personally convinced that omega matter must be 1, we just hadn't found it yet. But when I sat down to look at all the papers that had recently been written, all the data that was collected, the talk I ended up giving said, you know, something is going on. We do not live in a universe where cold dark matter makes omega matter equal 1. Something weird is going on. Either omega is not 1, either we do not have quite the critical density, or perhaps it's not all cold dark matter. Maybe there's a mixture of cold dark matter and hot dark matter, or perhaps there was something weird in the early universe that made galaxies form in a strange way, or maybe there's more stuff than just matter in the universe. Maybe there's this stuff which these days we would call dark energy. So in late 1997, we were getting desperate. We had a whole bunch of things on the table for what could possibly explain the data. We didn't know which one of them was right. So what do you want to do to resolve this? You want to weigh the universe. You want to find out how much energy density there is in space, but you want to weigh the whole universe. You don't want to just weigh a bit of it here and there, because you could always be missing something in between. So how can you weigh the entire universe all at once? It turns out that there are two techniques that you can use. One is to actually directly measure the spatial curvature. If you measure the spatial curvature, if you measure k, you can find out whether the density that you have is only 30% of the critical density or whether it's 1. We'll talk about that in the next lecture. The other way is to measure the deceleration of the universe, to measure how the expansion rate of space changes as a function of time. So this is something that you would expect to happen in an ordinary cosmology. It's true that the universe is expanding, things are moving apart, but while they're moving apart, the different particles in the galaxies, the ordinary matter and the dark matter, is pulling on all the other particles. Stuff is exerting a gravitational force, so you expect that expansion rate to gradually slow down. If there's enough stuff, it will in fact recollapse. That would be if omega was greater than 1, if we had more than the critical density. So if you measured precisely the rate at which the expansion of the universe was changing with time, that would tell you the total amount of stuff in the universe. The challenge is just to actually do that. It's very difficult. How do you measure the rate at which the expansion of the universe is changing? How do you measure the deceleration of the universe? Well, you do what Hubble did, but you just do it better. Hubble found the expansion of the universe by comparing the velocity of distant galaxies to their distances. So Hubble's law that tells us the velocity is proportional to the distance is always going to be valid in a small region of the universe, cosmologically speaking. But when you get out to a very, very far away galaxy, now you're looking at a galaxy that was emitting light from the distant past by the time it gets to you. You're actually probing what the universe was doing at an earlier time, because light moves at only 1 light year per year. Therefore, if you measure the distances and redshifts, the apparent velocities of galaxies that are very, very far away, you can see whether or not the expansion rate has changed. You can measure the acceleration or deceleration. So you want to do what Hubble did. You want to use standard candles. If you have some object whose brightness is fixed, you know how bright it is, then by seeing how bright it appears to you, you can figure out how far away it is. That's the basic idea of a standard candle. For Hubble, the standard candles he used were Cepheid variable stars, pulsating stars for which you could figure out from the period of pulsation how intrinsically bright the star was. The problem is that Cepheid variables are not that bright. They're the brightness of ordinary stars. You can't pick out individual Cepheid variables that are in very, very distant galaxies. Instead, you need a much brighter standard candle. So eventually what you appeal to are supernovae, exploding stars that are incredibly bright. Here's an image of one of the most beautiful supernovae you'll ever see. This is supernova 1994D. And you can see that there's a galaxy. The supernova is in the bottom left. That is a star in that galaxy. That is not a nearby star in our galaxy. The brightness of that supernova is comparable to the entire brightness of the galaxy behind it. It's billions of times the brightness of an ordinary star. That's the good news. The bad news is that they're rare. You don't see supernovae all the time. You can't predict them. In a galaxy the size of the Milky Way, you're only going to get about one supernova per century. The other problem is that supernovae are not standard candles all by themselves. They are not all the same brightness. There are different kinds of supernovae. In fact, you remember that we mentioned when we were talking about machos, how you create neutron stars, that there's a type of supernova called a core collapse supernova. You have a bright, heavy star burning nuclear fuel. The nuclear fuel burns out, and the core of the star just collapses. It explodes off the outer layers, and that is a type 2 supernova. Clearly, for different masses of stars, when they collapse, their brightness is going to be different. Type 2 supernovae are not standard candles. But from the name, type 2 supernovae, you might guess there's something called the type 1 supernova. In fact, there's various different kinds of type 1 supernovae, and there's a particular type called type 1a that can be used as standard candles. A type 1a supernova is a very different object than a type 2. A type 1a comes from a white dwarf star. So a white dwarf is what you get when a medium mass star gives out its nuclear fuel. It just settles down to be a white dwarf. But imagine that you're lucky and you have a white dwarf star which has a companion. There's another star next to it which in the course of its evolution grows, and the white dwarf begins to accrete some of the mass from its companion. Here's a picture of an artist's conception of a white dwarf getting mass away from a nearby star, and so the mass of the white dwarf gradually grows and grows and grows. But there's a limit. White dwarfs cannot be arbitrarily massive. Eventually, the gravitational field will become so strong that the white dwarf collapses. This limit is called the Chandrasekhar limit, and it's the same for every white dwarf everywhere in the universe. So you can see, you have a hint that something in fact is a standard candle. The place where the white dwarf collapses and the outer layers are blown off forms a type 1a supernova. It would not be surprising if every such event was more or less the same brightness. And it's true, they are plausibly standard candles. Type 1a supernovae could be approximately the same brightness. But there's various problems associated with the idea of using type 1a supernovae to measure the acceleration or deceleration of the universe. First, type 1a supernovae are not precisely standard candles. By looking at nearby supernovae, people noticed that type 1a's differed in brightness by about 15%. 15% doesn't sound like that much, but we're trying to look for a very, very subtle change in the expansion rate of the universe. Every 15% counts. The real breakthrough in this field came when Mark Phillips, in the late 1990s, realized that just like Cepheid variables, type 1a supernovae have a period luminosity relationship. The supernova doesn't pulsate, but it does go up in brightness and then go down. And what Phillips realized is that the time it takes to decline in brightness told you what the maximum brightness was. The type 1a supernovae that are the brightest are those that take the longest to decline. So if you measured not only the maximum brightness of the supernova, but also how it evolved, how the brightness declined as a function of time, you could really pin down that overall brightness to better than 5%. Then you have something that is a good enough standard candle to measure the deceleration of the universe. The other things are more like worries. One is, how do you know when you observe a supernova very far away that they were just as standard in the early universe as they are today? That is something we're going to have to deal with by taking a lot of data and trying to figure out what the physics behind these objects is. But more importantly, how do you find them? You could look at a galaxy and stare at that galaxy for 100 years, and then you have a 50% chance of finding one supernova. No one is going to give you telescope time to do that. You need to come up with a better technique. The thing is that only in the 1990s did astronomical technology evolve to the place where we could find a whole bunch of supernovae all at once. So people developed techniques using large CCD cameras. CCD is a charged coupled device which allowed you to take an image of a fairly wide swath of the sky. You want to take an image that is deep enough to get lots of galaxies, but wide enough that you get a whole bunch of them, so you get galaxies at different redshifts in great numbers. And what you do is, you notice that the rise time of a supernova, the time it takes to go from being dim to being very bright, is a couple of weeks. That turns out to be a very convenient time. You take an image of some region of the sky with literally thousands of galaxies in it, and then you come back again a couple weeks later to take another image. In fact, you can do the first image at new moon, where the sky is the darkest, and then you take the next image at the next new moon. It works out perfectly. Then you want to compare these two images to look for one of the galaxies getting a tiny bit brighter. So this picture is a little bit of a fake, because this picture is a better than average view of what such a supernova discovery looks like. That's because this picture is from the Hubble Space Telescope, not from the ground-based telescopes where most of this work is done, but you get a feeling for what's going on. You see an image on the left of the deep field taken by the Hubble Space Telescope, and another image of the same region of the sky taken several years later. You can tell that there's a supernova in the second image because there's an arrow pointing to it. That's the nice thing about these images. There's always arrows pointing to where you care about. In this case, the arrow points to a fairly dim red dot, which you can zoom in on and find that it is in fact a supernova all by itself. This is a very distant supernova. This is an especially good example, but using this kind of technology you can find supernovae by the dozens. So this project of finding a whole bunch of supernovae, type 1As, using them to measure what the universe was doing at earlier times, was undertaken in the 1990s by two different groups. One group was centered at Lawrence Berkeley Laboratory and was led by Saul Perlmutter. The other group was scattered around the globe. It was not really centered anywhere, but the leader of the group was an Australian astronomer named Brian Schmidt. So here's a picture of Brian Schmidt and on the left, Saul Perlmutter on the right, arguing over whose universe is accelerating or decelerating faster. It was a mostly friendly rivalry between the two groups. Perlmutter's on one side, Schmidt's on the other. Schmidt's group involved a lot of people. Adam Rees, who is now at the Space Telescope Science Institute, was the lead author on the most important paper. Bob Kirshner, who was at Harvard, was both Brian Schmidt's advisor and Adam Rees's advisor and sort of the intellectual godfather of the team. And Alex Filipenko was a prominent member of the team who is most famous for giving teaching company lectures on modern astronomy that I encourage you to have a look at. So it was important that two groups were doing it, because if only one group did it, nobody would believe them. If two groups do it and they get the same result, then people are ready to think that something is going on that's on the right track. Indeed, it was in 1998, only a couple of months after I gave my personal talk in 1997 when I said something is going on, that in the supernova groups in 1998 announced that something was going on, namely that the universe was not decelerating at all. It was accelerating. It was expanding faster and faster. The correct image of the universe is one in which galaxies have a velocity that is increasing as a function of time. This came as a great surprise. Most people did not expect we would live in an accelerating universe. The Schmidt group, in fact, had a subtitle, Searching for the Deceleration of the Universe. What they found was the acceleration of the universe. So you had a very strange situation where, on the one hand, the result was a complete surprise. On the other hand, it made perfect sense. The reason that people were willing to believe this result, besides the fact that two very good groups got the same result, was that it made things snap together. It answered a lot of questions all at once, as we will explain. However, the fact that the universe is accelerating is a physical challenge. It's not what you expected. There's an intuitive argument that as the universe expands, it should be decelerating because particles are pulling on each other. If particles should be pulling on each other, how in the world do you explain an apparently observed phenomenon that the universe is accelerating rather than decelerating? The answer is you need something besides particles. You need to invent a new kind of stuff. If the Friedman equation is correct, and the universe has nothing in it but matter and radiation, it doesn't matter what kind of matter and radiation you have, the universe will necessarily be decelerating. So either the Friedman equation is not correct, according to these data, and we will explore that possibility later, or there is something in the universe that is neither matter nor radiation, and we call that stuff dark energy. So what does dark energy mean? We use the word dark energy, it sounds a little bit mysterious, but I want to emphasize that even though there's a lot we don't know about dark energy, it's not just a placeholder for something going on we don't understand. The dark energy really does have some properties that are absolutely definite and need to be part of any theory of what the dark energy is. First, the dark energy is smoothly distributed through space. It is more or less the same amount of dark energy here in this room as it is somewhere in between the galaxies. At the very least, dark energy does not clump noticeably in the presence of a gravitational field. The reason why we know that is that if it did, we would have noticed the dark energy before when we measured the energy density of galaxies and clusters. By gravitational lensing and by other means, we would have seen that there is more energy here than can be explained by the matter, and that would be the dark energy. But we don't see that. The dark energy is the same amount inside a cluster as outside a cluster. That's why we didn't see it when we looked with gravitational lensing and dynamical means. So you might guess that the dark energy could be some form of radiation, that it could be something that is moving very quickly. If something is moving very quickly, like photons or neutrinos, it would not cluster into galaxies and clusters, so that would be smoothly distributed just like the dark energy. But the second important property of dark energy is that it is persistent. The energy density, the number of ergs per cubic centimeter of the dark energy, doesn't change as the universe expands. That's the opposite of what radiation does. Radiation loses energy rapidly as the universe expands. For dark energy, you need something that doesn't go away. It is the fact that dark energy is persistent that explains the acceleration of the universe. That's why we're convinced that the dark energy is really something different. It's not a kind of particle that is pulling on other particles. The dark energy is a kind of field, a kind of substance, a kind of fluid that fills space, and its energy density doesn't go away as the universe expands. But this is asking a lot. This is going around saying, okay, we've discovered some stuff that is completely unlike ordinary matter, dark matter, or radiation. Nevertheless, over the course of 1998, people began to buy this story fairly quickly. Why are astronomers, who are by nature quite skeptical people, willing to believe this remarkable claim? The real point is that it made everything suddenly make sense. Like I said, in 1997, things were becoming difficult to understand. We had a prejudice that omega matter, the density in ordinary stuff plus dark matter, should be 1, that we should have the critical density. But the observations simply weren't consistent with that. Plus, there were other problems that made the universe in which we believed not quite make sense when compared with the data that we had. One problem was the age problem. Given an amount of stuff in the universe, and given the Friedman equation, you can calculate how old the universe should be. It's an absolute requirement that the universe should be older than the stuff inside. When people calculated the age of the universe, and when they compared it to the ages of the oldest stars, they were often getting an answer that the stars were older than the universe. That didn't quite make sense. There were large error bars on that. It was not a very hard and fast conclusion, but it still made you worry that we were missing something. In an accelerating universe, the universe today is older for a given value of the Hubble constant than it would be in a decelerating universe, so it made the age problem go away, just like that. Another problem was large-scale structure in the universe. If you had a universe with nothing but matter in it, and the matter was the critical density, you form a lot of structure. There's a lot of matter around, it clumps very easily, and you have more structure in that hypothetical universe than we seem to be finding in the universe which we observe. You could explain this by saying that we don't have that much matter, that we don't have the critical density. But another way to explain it is to imagine there's something that doesn't clump. There's some dark energy that is smoothly distributed. It doesn't contribute to the growth of large-scale structure. Finally, there is this business about the critical density. Like I said, there was a prejudice on the part of theorists that the critical density was the nicest value for the total density to have. They were therefore hoping that observers would continue to find more matter, even though the observers were telling them, no, we haven't found any more. It turns out that once you find that the universe is accelerating, and you invoke the presence of dark energy as an explanation for this acceleration, you ask, well, how much energy do you need in the dark energy? And the answer is about 70% of the critical density. In other words, the really nice thing about the dark energy was that it provided exactly enough energy to make the total energy density of the universe equal the critical density. So it wasn't just that we had found a new element of the universe, it's that we had found what was apparently a complete picture, a complete inventory of the universe. So this is where this pie chart that we began our lectures with comes from. We have what is now called a concordance cosmology, a view of the universe in which 5% of the stuff in the universe is ordinary matter, 25% is dark matter, and 70% is dark energy. That simple set of ingredients is enough to make the universe flat, to be the critical density, to get the age right, to correctly explain large-scale structure, the acceleration of the universe, the cosmic microwave background, and get the matter density right in galaxies and clusters. That is a lot of observations that come from a small amount of assumptions. That's why people were so quick to jump onto the concordance cosmology bandwagon. It also tells us something about our place in the universe. Not only are we not, like Aristotle would have it, sitting at the center of the cosmos, we are not even made of the same stuff as the cosmos. We're only 5% of the universe. The kinds of things we're made of are only 5% of the energy density of the stuff in the universe. This is a big deal. It's a sufficiently big deal that it was recognized by Science magazine in 1998 as the breakthrough of the year. And they invented a nice little picture of Albert Einstein blowing new universe bubbles with his pipe to illustrate the fact that this dark energy was in fact something that Einstein himself had contemplated, as we will talk about in later lectures. Of course, even though it makes everything fit together, the dark energy and its role in the concordance cosmology are still dramatic claims. We would certainly not accept the evidence of the supernova data as sufficient to believe in this dramatic claim. We want to check things. For one thing, we want to check that the supernovae are telling us the right thing. For example, the statement that the supernovae indicate the universe is accelerating is just the statement that very distant supernovae are dimmer than we would have thought. So you can invent much more mundane ways to make supernovae dimmer. For example, maybe there is a cloud of dust in between us and the supernova that is actually just scattering some of the light. That is absolutely the kind of thing that the supernova groups took very seriously. The point is that when dust scatters light, it doesn't scatter every wavelength equally. It scatters more blue light than red light. So the light from the supernova would get reddened if it passed through dust. One of the things that the supernova groups did is to check very carefully for reddening and for other alterations of the spectra of the supernova they were looking at, and they didn't find any. They also checked that the behavior of the supernova they observed was the same, whether they came from small little galaxies or big galaxies, whether they were in clusters or outside clusters. There was no environmental effect that was leading to the supernova being different one place or another. The real killer check, however, on this picture of the universe would be to make a prediction using it and then to go measure that prediction. So there is a prediction made from this concordance cosmology. If 5% of the universe is ordinary matter, 25% is dark, and 70% is dark energy, and it all adds up to the critical density, then the spatial curvature of the universe should be zero. The universe should be spatially flat. So far we haven't talked about any observational check on that, so the next lecture will take us through how we know whether or not the universe is spatially flat, and the answer is yes, it is spatially flat. In other words, even without the supernova data, something is 70% of the energy density of the universe, and that something is the dark energy. So that's good news. It's good news that we understand something new about the universe. 70% of it is dark energy. The bad news is we don't know what that stuff is in some deep level. So in addition to making sure that we're on the right track, that there is dark energy, Theoretical physicists are now faced with the task of explaining what the dark energy is, where it came from, what it might be going into, how it can interact with other stuff. There is a simplest guess, which is Einstein's idea of the cosmological constant. We will take that guess seriously, but we will also look at alternative explanations to see which one fits the best.